Good morning. We have been looking at influence lines for the last couple of lectures, and today we're going to continue looking at influence lines. If you remember, in the first lecture I introduced you to the concept of influence lines, what an influence line was. Then we looked at how to get the influence line for structures, and we saw that there were essentially two methods. One was the direct approach, in which you use equilibrium, to obtain the influence line. The disadvantage of this method is that you need perforce a statically determinate beam or frame, whatever you want to call it, before you can use equilibrium. Secondly, it's a more time-consuming procedure, obviously, because you have to evaluate every response quantity and you have to get the expression for that response quantity as the load moves along the path that it is supposed to move. Therefore, we saw that the Mueller-Breslau principle, which actually operates on, is based on the method of virtual displacement. The Mueller-Breslau principle was an easy way of getting the influence lines. Now, we also saw that the Mueller-Breslau principle can both give a qualitative and a quantitative assessment of the influence line of any response quantity for a statically determinate structure. But when we came to statically determinate structure, we saw that the Mueller-Breslau principle can only be used to get the influence line in a qualitative fashion. Quantitatively, the Mueller-Breslau principle cannot give the influence line, and therefore we saw that to get a qualitative assessment, Mueller-Breslau principle is okay, but to get a quantitative assessment we have to go back to the direct method. The direct method is based on equilibrium, and we saw an example last time as to how, for a specific structure, because we knew how to evaluate the fixed end moment, and the fixed end moment directly was the bending moment, we could get a statically determinate structure, and we could solve it. Now, unfortunately, that was a very specific case, because we looked at a specific problem where we had a single span beam with one fixed and one pinned, and therefore we knew the fixed end moment, and therefore the fixed end moment was directly the moment itself, bending moment at that particular point, and therefore from that we directly could get static equilibrium. However, it is not always true that this is valid. So today we're going to look at influence lines and it's going to be statically indeterminate structures, and somewhere where you couldn't, by finding out fixed end moment, directly get the statically determinate beam. In a single span beam it wasn't a problem. As soon as we go into multi-span beams, you cannot do it. So how do we, but then the direct approach is the only approach to get the quantitative assessment of the influence lines, and therefore we have to figure out how to get a statically determinate structure where equilibrium can be used for multi-span beams or more complicated structures. So let us look at this, and this by the way is the 38th in the series of lectures for this particular course that I have done. Let us look at the problem. So this is a two-span beam, and we have to find out the influence line for various parameters. I'm going to define some responses for which we'll have to find out the influence line. And today we are going to see how this can be applied to get the influence line, both qualitatively as well as quantitatively. Okay. Now let me put a few of the response quantities. Let's say, obviously in this particular beam, the moving load is going to go from A to B to C. Okay. So let's look at R A. Let's look at R B. Let's look at R C. And let's look at bending moment at B. Let's just do these three, okay? These four. This kind of bending moment actually implies that it's this way. Okay, this is the internal positive, and that's why this is also positive. Okay, because this is the right face, this is this way, this is the left face, this is this way. Okay. This is the internal force, this is the external force that balances the internal force. And note that whenever we do, we have to externalize all forces before we can apply Miller-Breslau principle. Okay, so let's see how we solve this particular problem. First, qualitative. So we're going to do qualitative influence lines, and we'll be using Müller-Breslau principle. Okay, so let me draw this. For RA, this becomes this way, pinned, and therefore, and then you have to give a unit displacement. Let me draw that using the red pen. So you get a unit displacement here, and then this is for RA. Let me do it for RB. RB would be, sorry, this is the mirror. See, understand that all we are doing is giving unit displacement. It's the same principle whether it is a statically determinate structure or whether it's a statically indeterminate structure. Because what you do, Miller-Breslau principle says, release the point that the response that you are, or the restraint corresponding to the restraint response that you are trying to find out, give it a unit displacement, and the deflected shape of the structure is going to represent the influence line. Okay, so therefore this represents influence line. Note something interesting. in this particular case, you will see that this is going to be symmetric. This side and this side are going to be identical. Here, this is going to be 1. There's going to be a lot more displacements here than are going to be here. Okay? Here, this displacement, this displacement, this displacement, all the same. Okay, this is equal to this is equal to this. If they are the same, it's symmetrical. Okay, that comes from the boundary end conditions being symmetrical. You're giving a load, displacement at the point. Obviously, it's going to be symmetrical. Now, let us look at for RC and bending moment. So, remove the restraint at C, this is for RC, give it a unit displacement and find out the deflected shape. You will notice that RA and RC have just the opposite . Okay, they have just the opposite. We will see that later when we do a quantitative analysis. I am just showing it to you because, again, this and this are just the opposite of each other, and therefore what we got for RA, which was this and this way. So between AB, whatever the deflections are, and between BC, whatever the deflections are, for RA, those are going to be between AB, which is what between B and C, and it's just the opposite. Okay. And finally, for the bending moment at A, B, C. And what we have to do is give it a pin and make it go this way. So what actually happens is again, this is going to be symmetrical about point B, and I don't know what this value is. However, I know that this has to be equal to 1. Okay, because again, MB, right? So bending moment at B, and so therefore I have to give a unit displacement corresponding to the response quantity, and so therefore this way it goes. Why does it go this way? Because you look at it, the moments do this, so it's going to go this way, and this relative between the two tangents have to be equal to 1 at this point. Okay, so this gives you the Mueller-Breslau principle, gives you the qualitative assessment. Okay, now the question comes, how do I quantitatively assess it? So essentially, for quantitative assessment, what do I need to do for the quantitative assessment of influence lines? Remember that the only way that you can do quantitative assessment is by using the direct equilibrium approach. So for direct equilibrium approach, for something like this, note something, that if I know in this particular case A, B, C, for both member AB and BC, for example, if I knew the bending moment at B, would both AB and BC be statically determinate? Note that if I knew the bending moment at B, AB and BC would become statically determinate. So therefore the entire thing hinges around finding out the bending moment at B. But how can I find out the bending moment at B? Okay? Well, the only way I can find out the bending moment at B is to analyze the statically indeterminate structure and find out the bending moment at B. Which are the approaches that we know? The flexibility approach, okay, the stiffness approach, or call them the force method and the displacement method, or the moment distribution method. Now note that both the force method and the displacement method, what do you find out first? Do you find out the bending moment directly? No. You first find out actually the displacements corresponding to the degrees of freedom in both the force method and the displacement method. Or in the force method you find out a redundant force and from that solve the statically determinate. In the displacement you find out the displacement. In other words, you do not directly find out any quantity without first finding out something else and then deriving it. Okay? But you see, in this particular case, we don't need to know that under the load what is the displacement. We don't need to know under the load what would be the support reaction at C. I may not want to find out the influence line for support reaction at C. You see, you understand the point. And you have to understand another point, that you actually have to solve this using the force method and displacement method. You would have to actually solve it for different positions of X and find out the redundant or the displacements. So it's actually solving many force methods and displacement methods. Okay, and that is not a very, you can do it. I'm not saying you cannot do it, but it's not an efficient way of finding out an influence line, because in an influence line, all I'm interested in is what are the ordinates of the influence line so that I can find out the particular response quantity. And the best method which directly finds out the bending moment at B without finding out something else is the moment distribution method. So therefore, what we do actually is, see, the whole thing over here is to make it statically determinate structure. And we know here that if we knew the bending moment at B, new bending moment, it would be a statically determinate structure. So we use the moment distribution method. Now how do we use the moment distribution method? Well, let's see. What we do over here is actually, in the moment distribution, what do? You actually fix this, don't you? Now these you don't fix because these are ends. Remember, we can do the modified 3 by 4 I upon L and use the modified member, if you remember. Okay. Now in this particular case, what we see is that, look, now the load could be between A and B. Suppose the load were between A and B. What would happen? You would get fixed end moment at BA. Okay? And what would be the fixed end moment BC would be equal to 0. So you get a fixed end moment, and then what would you do? You would release it, you'd put this fixed end moment, find out, etc., etc. So while the member is between A and B, we could actually find out the bending moment at B by moment distribution, by first finding out fixed end moment at BA and then doing it. Now suppose it's between B and C now. It's not here, it's here. Now what happens? In that particular case, the second case, between A, B, and now the member is between BC, then fixed end moment at BA is equal to 0 and fixed end moment at BC is what you calculate. And the point here is, if you could somehow find out the bending moment at B in terms of the fixed end moment, either BA or BC, depending on where the load is. Then you see, can I find out the fixed end moment given a load? Fixed end moment, I can find it out. It will be, if this is X, then this will be in terms of X and L, etc., etc. This is L, this is L. Okay? This also would be in terms of X and L, etc. So in other words, given a position of the load, I could find out the fixed end moment. And if I could find out bending moment in terms of this and this, then I could find out this in terms of X and L, and then that's it. We've solved the problem. Because then once I know bending moment, okay, for a given position, I can find out everything else. Okay? So the whole point really boils down to this. Okay? And therefore, all we need to find out is, for example, possibly, if we could get something like this, is equal to C1 fixed end moment at BA plus C2 fixed end moment at BC. If we could get an expression like this, and we knew C1 and C2. Note that when the member is in AB, I know that fixed end moment BC is 0, this would drop out. And since I know this, and I can find this in terms of X by L, I can find out bending moment and make it a statically, both AB and BC are statically determinate structures. Okay? Suppose it's between B and C, then this would be 0 and this would kick in. So all I need to do is really find out C1 and C2. If I can find out C1 and C2, I've solved my problem. And therefore, what we do now is the following. What we do is, well, we find out C1 and C2 separately. How? Well, all I need to do is apply 100 units fixed in and find out what bending moment at V is using moment distribution. Okay? If whatever I find this, then C1 is equal to BMB upon 100. Then next, this is separate. I give 100 units fixed end moment at BC and find out bending moment at B using moment distribution, and then C2 is going to give me bending moment upon 100. So this first case, this second case, two different loads and two different moment distributions. Okay, so let's do that. So I'm going to apply. So I'm going to do the moment distribution. Moment distribution is simple. Go back and look at your thing. You will have A, B, B, A, B, C, C, B. For this, it will be 3 by 4 I by L, 3 by 4 I by L, 0.5, 0.5. What's the fixed end? First case, fixed end moment, I'm applying plus 100. Okay, 0, 0, 0. I'm only applying a fixed end moment at BA. Because why? My whole goal here is to actually find out the C1. Okay, which relates bending moment to bending moment at B to the fixed end moment at BA. Okay. So how would I first is going to be distribution minus 50 minus 50, and look at this, nothing's going to happen here because no carryover there. It's already 3 by 4 modified. So what we get is plus 50 minus 50. So in other words, moment, the bending moment BA is equal to 0.5 of the fixed end moment. Instead of writing that down, I'm going to write it in this fashion. MBA and MBC is equal to 0.5 fixed end moment at BA. Let us now do the same thing. Another moment distribution where A, B, B, A, B, C, C, B. And now I'm doing the fixed end moment at BC. So I'll do plus 100. This is 0, this is 0, this is 0. Again, the half, half. So this is going to be minus 50, minus 50. And that's done it. This is minus 50. Plus 50, and therefore this is going to be minus 0.5 m fixed end moment, and this is going to be plus 0.5. Note, these are the bending moment at BA and BC. These are the fixed end moments. In other words, we have found out the moments in terms of the fixed end moment at BA and BC. Okay, so this expression now we have. Now, we have this situation. No, wait a minute, this is this way. A, B. If the load is at X, so if X is less than L, that means load on AB, then the fixed end moment at BA is equal to, think about it, it's going to be x squared L minus x upon L squared. Sorry, this is minus because it's anti-clockwise. This is also minus half L minus x squared x upon L squared. You do it. I have done enough of this to let you know how you can find this out directly. Okay, so I'm not going to this is the fixed end moment if x is less than L. And if x is greater than L, then fixed end moment at BC. Okay, note that here I'm going to be taking x, this is B, this is C, and x is actually from this end, so this is going to be equal to x minus L. X is from A, okay, and this is going to be 2L minus x, because x, remember, is going from 0 to 2L. Okay, so for this fixed end moment is going to be equal to, again, B is going to be positive, so it's going to be 2L minus x the whole squared into x minus L all over L squared plus half x minus L the whole squared into 2L minus x all over L squared. Okay, so we've got the fixed end moments, etc. I'm going to write them down again here, that if x is less than L, that is load on a B, then fixed end moment at BA is going to be equal to minus x squared L minus x over L squared minus half L minus x the whole squared x upon L squared, and fixed end moment at BC is equal to 0 if x is between L and 2L, that is load on BC, then fixed end moment BA is equal to 0 and the fixed end moment BC is equal to 2L minus x the whole squared x minus L upon L squared plus half x minus L the whole squared into 2L minus x upon L squared. And finally, we also know that the bending moment at BA is equal to 0.5. This is, I'm denoting as MBA, this I'm denoting as MBC, this I'm denoting as MBA, and this I'm denoting as MBC. Just for like writing down, the reason I'm doing this is not for anything else. It's still the fixed end moment. It's just that writing down long expressions does not serve a purpose. I'm using a smaller notation, that's all. There's nothing, there's no reason, no other reason for this. And bending moment at BC is equal to minus 0.5 MBA plus 0.5 MBC. Now we have these, and finally, if I know the moments, then let us see what we can do. Let's look at it. I'm just putting this just for this thing, but essentially this is, remember, AB, where we know M MBA. Now if I know MBA, let's look at what I can find out. I can find out what? I can first find out, and by the way, let's assume that the load is in. So if we look at this, then you can see that RA, and I'll call this VB because this is not really any this thing. This is the open section where this is the support B. Okay, so we made a cut, and then we have B, C. Okay, so here if I have like this, then this goes this way. Okay, and this is MBC. Okay, so, and this is RC, and this is VB minus, this is just to the other side, this is VB plus, and if you look at it, this one is going to be positive this way, this one is positive this way, and therefore this one comes down here and this one goes up here. And so if you look at, let us see, RA directly is equal to RA. Okay, so we can find out the expression for RA if x is between 0 and XL, then RA is equal to one aspect of it is 1 minus x over L. Okay, that is directly from the load. The other one is from the bending moment, and this is going to be this upon L. Okay, so that is RA. Let us look at what happens to VB minus. VB minus is equal to x by L minus MBA. Okay, now let us look at what happens here. What is our C equal to? Our C is equal to just directly so our C is going to be minus MBC by L. VB plus is equal to MBC by L, and since our B is equal to VB minus VB plus, our B is equal to VB minus VB plus, so it will become x by L minus MBA by L minus MBC by L. Okay, now note one thing that we'll come to it, and I don't care right now. And also, if you look at bending moment at B, the bending moment at B is equal to MBA, because this is positive, this is, or I mean, the bending moment at B is equal to MBA or minus of MBC. In fact, MBA is equal to minus of MBC, and you will see that since MBA and MBC are minus, this actually ends up being x over L. Okay? So, let us now proceed. This is if the load is between A and B. Now, these are the expressions. We found out everything. We found out RA, RB, RC, and the bending moment at B expressions. Now, we also need to find out if L is between X and what happens then. Then you see what happens here is this, that as far as A and B are concerned, then we have this. So this remains as MBA, this is VB minus, this is RA, this is RB, this is going to be this way, this is going to be this way, this is going this way, this is going this way, and on this side I have MBC, this is MBA, MBC, RC, and now this position such that this is 2 minus L upon X. Okay? So this is when X is between L and 2L. Then what can we say? What would RA be equal to? You will see RA is directly equal to MBA by L. VB minus would be minus MBA by L. And then RC would be equal to this would be X minus L. Okay, so RC would be X by L minus 1, okay, and this is from the loading itself, and then the other part is minus MBC by L. Okay, that is RC, and then VB plus, that is this one, VB plus. VB plus would be equal to 1 minus this, so it would be essentially 1 minus this will be 1 minus this will be 2 minus X by L, that is from this part, and plus MBC upon L. And this implies that RB is equal to VB minus, so this becomes VB minus this, so this becomes minus 2x upon L, minus 2x minus 2L, and then minus MBA by L minus MBC upon L, which basically means minus 2 minus x over L, which is essentially x over L minus 2. And bending moment B is still continues to be MBA or minus MBC. So now we have all the expressions, and I will just illustrate what these would be for a particular value. So let me just do it. I'm not going to do it. You can obviously find out more details as we go along, but I'm just going to do this for specific quantities. So this is going to be x, and I'm going to say 0, and then no L by 4, so I'll just do it L by 2, then L, 3L by 2, and 2L. The reason why I'm only doing these, of course you can do it for smaller, you just have to evaluate it. Okay, you should be able to evaluate that. You can find it at as 1/8 of L. You can just try to find it at 1/8 of L. That can be an exercise for you to do. Okay, so that you can get a finer this thing on the influence line. I'm just doing it grossly. The first thing that we need to find out is the fixed end moment, and I'm going to put that as MBA. Okay, then I'm going to make fixed end moment at BC MBC. From that we can find out the moments at the ends BA in member AB. We can find out MBC, and once we find out these, then we can find out what can we find out? The quantities that we are interested in. RA, then RB, RC, and then I'll just draw another line. Bending moment at B. Okay, so now the first step is to find out these values, and I'm going to spread out all these in front of me so that I can find out each one of them directly. Okay, now when this is between 0 and L, this, and this is 0, and then when it's between L and 3L by 2, this is 0. This we have already done. Okay, now for this I know that this is also equal to 0, and here this is also equal to 0. Okay, so let me find out for L by 2. Okay, so if I find it out for L by 2, what would be the value? Just plug in this x equal to L upon 2, substitute it in, and you will see that you will get that this becomes 3L upon 16. Then plug in over here 2 minus 3L upon 16 because it's anti-clockwise. Okay, and this is going to be plus 3L upon 16. Okay, so let's now do this. So now this MBA we know in terms of the fixed end moments at BA and BC. So this is going to be 0, 0. Okay, and at what is the expression for RA when x is between L and L? Just plug it in. MBA is 0, so you get x equal to L, so RA is equal to 1, and RB is x by L, so that is 0. RC is minus MBC by L, that is 0, and the bending moment is MBA, which is 0. Okay, let us now find it out for this. Obviously MBA and MBC are equal to 0. RA is equal to 1 minus x by L. X by L is 1, so this is 0. RB is equal to x by L, so it's equal to 1, and C is equal to minus MBC by L, so this is 0, and bending moment is also 0. Let me find it out for here. This is going to be 0 and 0. RA, let me see what RA is. It's MBA upon L, so this is 0. What about RB? RB is equal to x upon L minus 2, x upon L, is going to be 2 minus 2, so this is going to be 0, and RC is going to be equal to x upon L minus 1, so this is going to be 1, this is going to be 0. And let me evaluate it here. Okay, so if we look at this, MBA is half of this, so this becomes minus 3L upon 32. What is MBC? It's minus MBA, so this is going to be 3L by 32. Okay, yeah, and where are we? This RA is going to be equal to, RA is going to be 1 minus x by L. 1 minus x by L is 0.5. 0.5 plus MBA by L. MBA is minus, and so this is going to be equal to 0.5 minus 3 by 32, so that's going to be 16, so this is going to be 13 by 32 positive. Okay, RB is going to be x by L, so x by L is going to be equal to half okay, and R now VB plus is actually this way, and this is this way. Okay, so VB plus, and so this is going to be this plus this, so you're going to have plus this, and so this is not x upon L, this is plus and plus. Okay, and the other point that I would like to make is that so MBC is this way, so RB is equal to this, and then this is proper. Okay, so this actually is equal to not just half, it's going to be this plus 6 upon 32, so that's 3 upon 16, so it's going to be 11 upon 16, and RC is going to be minus MBC upon L, so that's going to be equal to 3 by 32. Okay, positive. No, negative, sorry, negative here, because what you're going to have is, negative, because here you have this, so it's minus MB upon L, and the bending moment is going to be equal to 3L upon 32. Okay, so now let us go over here. This is going to be 3 by 16, so MBA is going to be minus 3L by 32. This is going to be 3L by 32, and therefore you get exactly the same values, 13 by 32, 11 by 16. Sorry, this becomes minus 3 by 32, this becomes 13 by 32, and this is 3L upon 32. Okay, this is the end, and if you look at this, you will see that RA is 1, so at this point, at the center point, it's 13 by 32, which is less than half as you expected it. Over here, it's minus 3 by 32, much less than this. This is what you expected. Okay, and it's 0 here, and 1 here. That's there. RB, if you look at it, RB is symmetrical, 0. 11 by 16, you would expect that. This is more than half. Okay, and 11 by 16, symmetric. And this one is just the opposite, and this is how it is. And if you look at bending moment, you will see that it is indeed correct. So, in other words, we have illustrated how to use moment distribution to get the influence lines qualitatively for a particular structure. I'll stop here. I'll continue over the next few lectures looking at other examples of this. Thank you.